Welcome. This presentation will be about modeling and simulation of the horizontal seat suspension system subjected to random vibration signals, prepared by Jereczek, Maciejewski, Krzyżyński and Królikowski, from Koszalin University of Technology in Poland. The presentation will proceed in the following order. First, a brief introduction and purpose of the research will be presented, then the object of the research will be shown and discussed. This will lead us straight to the identification of the parameters of the simulation model. At a later stage, the process of model verification will be presented, and we would like to end with a summary and conclusions. Nowadays, the importance of computer modeling is becoming more and more important every day. The global pandemic caused a significant decrease in the availability of mechanical components and technical devices. In order not to slow down the pace of technological development, scientists across the world often use modeling as an alternative strategy for new product development. This leads to a deeper understanding of the system under investigation without using real objects. At present, heavy-duty machinery is omnipresent for assisting employees and increasing their work efficiency. Unfortunately, their use introduces unwanted vibrations that can be generated when working machine moving at high speed over rough terrain. Mechanical vibrations have a negative effect on the human body, especially in the low-frequency range. Ongoing research on vibration reduction includes just linear models of the seat suspension, which often leads to an unreliable representation of the system dynamics due to natural non-linearity of its components. However, most of the active suspension systems are designed to reduce vibration only in the vertical Z direction. The authors of this presentation show a reliable simulation model of the passive horizontal seat suspension system. In order to reflect the physical object as much as possible, its nonlinear behavior is modeled and the unknown model parameters and identified experimentally. Furthermore, the system dynamics is investigated under random excitation at different vibration intensities. The horizontal seat suspension system under investigation is shown in figure. Such a passive system is equipped with 2 tension springs, 2 end-stop buffers, and a hydraulic shock absorber. A linear mechanism is responsible for the positive or negative movement x of the vibro-isolated object around its equilibrium position that is determined by the forces Fcx of 2 counteracting tension springs. The damping force Fdx is applied to reduce resonant vibration of the passive suspension, while the opposing forces Fbx of end-stop buffers are used for limiting the maximum displacement of a suspension mechanism. The frictional losses of moving mechanical parts, which are equipped with the needle roller bearings, are defined by the overall friction force Ffx. Random kinematic excitation Xs is applied to the suspension system that is generated along the longitudinal x direction of vibration exposure. The first equation is the equation of motion for the suspension system under study in terms of the equilibrium condition of the forces acting in the system, where m is the mass of vibro-isolated object, x is its longitudinal displacement. Fcx is the tension spring reaction force, Fbx is the reaction force of end-stop buffers, Fdx is the damping force of a shock absorber, Ffx is the friction force resulting from the relative motion of a suspension mechanism. The second equation is the reaction force of 2 tension springs defined just by the linear function because of such system components demonstrate a linear force increase as a function of the suspension deflection, where K is the equivalent spring stiffness, is the relative displacement of horizontal suspension system. Third one represent the force of end-stop buffers by the polynomial approximation of measurement results that are obtained during a quasi-static test of the seat suspension system, where xb defines the free stroke of a suspension mechanism without the contact with end-stop buffers. A, b, and c are constants that define coefficients of the cubic equation. The first 2 conditions take place when the relative displacement of suspension system is higher than the free stroke xb in negative direction. The last one is applied in the free range of suspension stroke when the vibro-isolated object has no contact with any buffer. Mathematical model of the shock absorber, equation 4, is also given as the nonlinear relationship between the damper force and its relative velocity, where is the relative velocity of suspension system, A, B and C are the coefficients of approximation function that are identified by means of experimental testing. The final equation describing the friction force generated by moving parts of a suspension mechanism, which is determined as a function of the relative velocity and is assumed to be divided for two different states of motion. The first state is responsible for low velocity motion, static friction, and the second one is activated when the suspension system is in motion, kinetic friction, over a specific velocity, where FFS and FFK are the measured values of static and kinetic friction force, respectively. The function marked as y describes a hysteresis behavior of the kinetic friction force and is calculated by using the algorithm showed below. Equation where is the turning point of a hysteresis, which corresponds to the specific location where the systems start moving in opposite direction. The value delta y with star defines the previous value of y until the turning point is reached. Last indicator is the saturation slope of the continuous transition, which is determined by the parameter. The force characteristics of a horizontal seat suspension are identified experimentally by using the test rig shown in figure. For this purpose, the lower part of a suspension system is driven by an electro-hydraulic shaker and the upper part of a suspension system is fixed or movable with the use of a force sensor. The movement of a seat base is measured by employing a linear displacement sensor. Based on these signals, the nonlinear force deflection and force velocity characteristics of each system component are evaluated under strictly defined test conditions. In case of the system identification, the seat suspension is investigated without any additional load due to prevent transverse forces that can possibly damage a force sensor. The stiffness characteristics of a horizontal suspension figure are determined during the quasi-static test. While the suspension system is subjected to kinematic excitation by a triangular signal with frequency 0.1 Hz and amplitude of 0.02 meters, damping characteristics of the shock absorber, figure B, are evaluated by measuring its reaction force as a function of the relative velocity. The sinusoidal signal of a constant amplitude plus 0.0125 meters is applied at different frequencies that correspond to the maximum velocities of 0.066 and 0.131 meters s. The hysteresis of the friction force, figure C, is measured while a triangular signal with an amplitude 0.002 meters and a frequency of 1 Hz is used. Such signal provides a constant velocity during the test and a fast switch between direction of motion. As shown in figures, the force of tension springs, figure tends to be linear within the suspension stroke of plus minus 0.015 meters and then strongly increases up to plus minus 0.02 meters because of the contact with end-stop buffers is occurred. In turn, the damping force, figure B, shows progressive characteristics of the shock absorber and velocity domain. Finally, the kinetic friction characteristics, figure C, points out the hysteretic behavior of a suspension mechanism when changing the movement direction. In order to solve the equation of motion including the forces of individual suspension components, the MATLAB Simulink software is used that allows for developing simulation models using graphical interface. The nonlinear differential equations are solved by employing the fixed-step method, Vygotsky-Champy algorithm. The sampling time of solving procedure is equal to 1 millisecond. For validation of the simulation data, the laboratory setup presented in left figure is used. The shaker with a hydraulic actuator generates vibration input for the horizontal seat suspension system under investigation. The input signal is similar to the white noise with varying frequency band between 0.5 to 12.5 Hz. The tests are performed for 3 different load masses, 30, 55 and 80 kg, and 3 different vibration intensities, WN1, WN2, WN3, of the excitation signal. The power spectral densities of considered input vibration are illustrated in right figure. As follows from the presented figures, the simulated and measured spectral characteristics are close to each other with relatively low error. In order to evaluate the performance of a simulation model in comparison with a physical object, the power spectral densities and transmission functions are determined based on the data recorded from vibration acceleration signals. The exemplary results for a horizontal suspension system loaded by mass of 55 kilograms are shown in figure. Red solid line as simulation result, and blue dotted one as measured. It should be noticed that with the higher vibration intensity, the resonance amplitude increases due to nonlinear behavior of the seat suspension system, figure B, D, F. However, the resonance frequency is approximately the same for a chosen mass load of 55 kilograms. The damp resonances of simulated and measured systems are occurred at the frequency of about 2 Hz, and for the higher frequencies a desirable vibration isolation is provided by the seat suspension. The presented in Figure 6 spectral characteristics prove that simulation model behaves in a manner similar to the physical object. In order to assess the simulation and measurement results, the seat effective amplitude transmissibility, seat factors, and maximum relative displacements of the horizontal seat suspension are compared quantitatively. The seat factor is one of the most popular indicators that is used to evaluate dynamic performance of the seat suspension. Such an indicator can be calculated from data measured in the test laboratory or can be determined directly in the workplace. The obtained simulation results show a high compatibility with the experimental results obtained from the test laboratory. Comparing the selected indicators, it is shown that the maximum error remains at a satisfactory level, achieving about 7%. The modeled system points out the best performance when the mass load of 80 kilograms is applied. Both simulation and measurement results show that the passive system efficiency is insufficient for vibration attenuation in low frequency range. Therefore, further system development is required, and the model described in this presentation will be a basis for developing a nonlinear control strategy, the active seat suspension. After testing a computer model, the developed control strategy will be implemented into the real system in order to improve the efficiency of a seat suspension in the longitudinal direction of vibration exposure. Future investigations will assist to provide progress in the field of horizontal seat suspension systems that allow to increase their comfort and safety. Thank you for your attention. This presentation was prepared by the authors, Bartosz Jereczek, Igor Maciejewski, Tomasz Krzyżyński, Tomasz Królikowski, as part of the conference. 26th International Conference on Knowledge-Based and Intelligent Information and Engineering Systems, concerned the paper titled, Modeling and Simulation of the Horizontal Seat Suspension System Under Random Vibration.